the characteristic impedance of a transmission line is going to be Z naught equals square root L over C, where L is the inductance per unit length of the transmission line. Remember, a transmission line is made up of a bunch of infinitesimally small inductors and capacitors. And then C is going to be the capacitance per unit length. And so what this sort of tells you is what dials can you tune in order to increase or decrease the impedance of a transmission line. And notice this is for a lossless transmission line. There's in a real transmission line, in a lossy transmission line, you would have also a resistance and dielectric loss term, but we're not going to worry about that for now. So okay, so let's consider like two transmission line architectures that you can have, and there are like many more. There's like many more, but this is just like two of them that you might see on a PCB. So this one is a microstrip architecture where you have your forward conductor on the top, and that's going to be the little trace here in gold, or colored gold. It'll be like copper. Then you have the dielectric, then you have the then the return plane underneath. And then so that's microstrip. And you also have strip line. So this is, you have two return planes sandwiching the forward conductor. And then you have the dielectric. The forward conductor is sort of like embedded in the dielectric. So that's going to be strip line. And so just sort of a quick precursor. If you look at the electric fields here, the electric fields for the microstrip case, they're going to be sort of, there's going to be like, they're going to be sort of concentrated under the trace, but they're also going to branch out from sides of the trace. And so those are going to be called the fringing fields, the ones that branch out. For a strip line, they're also going to be sort of concentrated in this on either side of the trace, but they're also going to spread out just like in the microstrip case. So those are going to be the fringing fields. And so the fringing fields matter more when we're talking about crosstalk. And so we're going to talk about that in another video. But the sort of the point here is you have this capacitive coupling between the forward conductor, which are, let me get a different color, the forward conductor, the orange there, and the return conductor, which, I don't know, blue. Return conductors are going to be blue. So going back to this equation, what dials can you turn? Well, let's see if we can increase the capacitance. That would decrease Z naught. So how do you increase capacitance? Well, again, you have your, I'll just redraw it. Let's look at microstrip because it's the same for a microstrip and strip line actually. So we'll just look at microstrip. If you make this physically wider, you're increasing the width of the trace. You're increasing the capacitive coupling. You have more capacity. You essentially are increasing the capacitance, and so that will bring down the characteristic impedance. That decreases the characteristic impedance of the trace. If you make a wider trace, you're changing the impedance. Alternatively, if you were to change the dielectric thickness, if you were to make the dielectric a lot thicker, well, we know that the capacitance will decrease with distance between the plates, like just on a regular capacitor. If you have certain spacing between the capacitors, if you were to increase the spacing, you decrease the capacitance. That's just the formula for finding the capacitance of something. The D is the distance is in the denominator. And so that's sort of, as you increase the spacing between these two conductors, you'll actually increase Z naught because you're decreasing the capacitance. And so the capacitance is in the denominator. So that's kind of, so those are two dials you can turn. As you increase the width or as you move the forward conductor farther away from the return plane, you can sort of change the, you can change the impedance of the trace. And so that brings us to this concept of controlled impedance. Because we're going to talk about how you don't want the impedance in the trace to change, because at each point that the impedance changes, what you see you'll see a reflected wave and a transmitted wave. Like if you have a trace, you have a trace and then suddenly it widens off into like a larger, well, into a larger width, then you'll have an incident wave coming in, but you'll also see a reflected wave coming out and a transmitted wave. And so these waves can lead to ringing, or they can cause other signal integrity issues, and so you don't want them to be there. So you want there to be a uniform impedance. You want the impedance to be the same, and often across the entire length of the trace. And often what this means you want to maintain a certain uniform cross section. Again, like the cross section is just going to be this thing that I keep on drawing. It's just I don't know why I keep drawing this over and over again. It's literally the same drawing, but okay, like this cross section, you want this to be uniform across the entire length of the trace. A uniform cross section for a transmission line will mean that you have a controlled impedance, and that includes the dielectric constant of this. If the dielectric constant of the dielectric were to change, then you would also change the characteristic impedance because you're changing the capacitive coupling. And so that's the concept of controlled impedance, keeping the impedance of the trace the same over the length of the line, so you don't change sort of so you don't create these reflections and other signal integrity issues. Now there are some cases in which the impedance will have to change. Whenever you go through a via, for instance, on a PCB, let's say, I'll choose the standard colors here. Let's say this is a trace on the surface layer, goes through a via onto the bottom layer. Altium usually shows like the surface layer, or like the top layer in red and then the bottom layer in blue. I guess this is not really red, but whatever. So when you go through a via, that is going to be a change in the impedance of that's a change in the cross section of the transmission line. So it's going to be an impedance discontinuity. If you go to a connector, if you have a trace and then it goes into a connector, the connector pins will probably have a different impedance, different cross section than the transmission line, different impedance. And so that's an impedance discontinuity. If you have a pad on like an IC, that'll also be an impedance discontinuity. Most of these you don't really often care about for what we're doing in YJSP. But if you're doing like really high speed stuff, then you do need to sort of look into all of these impedance discontinuities and see if the effects are tolerable, the effects that they create. And so in YJSP, at least, the biggest impedance discontinuity sort of related thing we're going to have to worry about is for digital buses, making sure that all of our making sure we have source series termination on all of our digital buses that need proper termination, which I'll talk about in a later video. But ultimately, the end goal is you want to control the impedance of traces where you have like very high speed signals